Hey everyone, welcome to our next section on rational numbers and rational expressions. And so hopefully you've had a chance to go through a little bit of factoring questions before to really solidify how to factor polynomial expressions and which tricks to use based on the type that you're given. That's going to be really relevant coming up here in the next couple of videos as we start to go through this unit on rational expressions. So remember that an irrational number, they're non-terminating numbers, so like 0.624653, which would just keep going on forever, and that a rational number terminates or repeats, like 0.62. So for our purposes in this unit, we're going to specify rational numbers that can be expressed as a quotient of two integers. So quotient is just like a fraction, like a division, and rational expressions can be expressed as a quotient of two different polynomials. So for example, we'd have something like, say, 2 over 5, or maybe it's x plus y over x, or maybe it's x plus 6x, x squared plus 6x plus 5 over x plus 1. In all three cases, we have these ideas of rational expressions because we have rational numbers that show up, or integers, I guess, that show up on the top and the bottom. So, why do we need to know about rational expressions? So there's a lot of everyday applications that use rational expressions. If we think about things like rate, if you've gone through anything, say like in physics class when we talk about distance over time, that would be a rate that would describe two different numbers, distance being, how far something goes over your time, how long it takes to get there. Formulas for something like light intensity, intensity of sound can be described as well as algebraic fractions that have numerators and denominators, and there's lots of other ones. If you could think of any maybe math formulas throughout your different math courses that you've taken that have fractions as equations, well then you're starting to build up this concept of rational expressions. So let's start to think about the following. Think what would happen in each of the following expressions when x is equal to 3 is substituted in. So in the first one, we're going to plug, wherever x is, we're going to plug in a 3 into that spot. So in each of the following, what I'd like for you to do is pause the video and just plug in x equals 3 into each one of them and just see what you get. So pause the video, give it a try, and come back when you're ready. Alright, so hopefully you had a chance to take a look. So here, if we're going to plug in x equals 3 into this, then we have 3 minus 7 on the top, and on the bottom, we're going to have 3 minus 3. And so what we end up getting here is negative 4 over 0. That presents a bit of a problem in itself because we know that, and if you're not quite sure, take a calculator. If we divide anything by 0, it gives us an error. Okay, we're trying to basically make groups of nothing. And so we're going to get this problem here where we can't do that. So we can't divide by 0. If I take a look at the next one, I run into this similar situation. So here I've got the same 3 minus 7, and then on the bottom I'm going to have 3 squared minus 9. So here I'm going to get negative 4 over, and then 3 squared is 9, and so 9 minus 9, I end up with the same problem where I get negative 4 over 0. So same thing, down here I'm going to get an error and because I'm dividing by 0. And as you probably guessed or have figured out, if you try the last one, I've got the same problem where I have 3 minus 7 over top of 3 squared minus 4 times 3 plus 3. And so that's going to give me negative 4 over, and again, 3 squared is 9, plus 3 more is 12. So 12 minus 4 times 3, that's 12 minus 12, which is going to be 0. So again, I get this error that's going to show up. So in all three scenarios here, I have different functions, and in each one of them, I'm getting a value that's causing this thing to terminate to 0. It's causing my denominator to be 0. So basically, in this equation, I have a lot of different values that could work in here, but I know that anytime I plug 3 into any of the denominator places, whenever x is 3, I get an error. And so that's going to kind of drive most of this lesson, is that idea that we get these error values. So when simplifying rational expressions, the most important thing to remember is that you cannot divide by 0. Division by 0 is impossible. Therefore, we have to put restrictions on the variable in our denominator. So we basically say that x cannot equal this value, or y cannot equal this value. It can't equal 0. These restrictions are also known as non-permissible values. So what are the non-permissible values for each of the expressions that are below? Again, I encourage you to pause the video, try them out, and come back once you've had a chance to just kind of see if you can figure out what x cannot be in the denominator spot in each one. Alright, so let's give it a try. So in the first one, do we see that if x is 0, then 2 times 0 is 0. If x is 1, I'm going to get 2. If x is negative 1, I'm going to get negative 2. So basically, the only thing that x cannot be here, x cannot equal 0. If x equals 0, then I have an undefined value or an error. So my restriction or my non-permissible value in A is x cannot be 0. Now, in my next one, x minus 7, what can I make x so that I have this 0 value? What can x not equal? What's my non-permissible values? So x in this case cannot equal 7. Now, in my last ones, really what I've been doing here is the same way we've been kind of finding roots so far. So really what I've been saying is x minus 3 cannot equal 0. And then I just treat that cannot equal sign just as a regular equal sign, and I solve for x. So in this case, I need to add 3 to both sides, and I can see that x cannot equal 3. On the other side, I can say, okay, 2x plus 1 cannot equal 0. 2x cannot equal negative 1. X cannot equal negative 1 over 2. So I've got 2 different non-permissible values here. I have x can't be 3 and x cannot be negative 1/2 in my last one. So if I have either of these values, I'm going to get a 0 show up in one spot, and then 0 times the other thing is going to give me 0 on the bottom, which is going to give me an error. So x cannot equal either of these 2 values. It will give me a non-permissible value. So a couple little memes that are here. We cannot divide by 0. I can't stress that enough. So there's just a couple little jokes here that just kind of go along with that. So congratulations, your math just destroyed a city. Divided by 0. And, dividing by 0, I warned you not to do it. And if you want to think about it like an 11th commandment, thou shalt not divide by 0. You cannot divide by 0. So the whole idea here is just trying to think of what x cannot equal. So some restrictions here, 3x over 5 plus x. Again, a couple different examples. Pause the video and try them out and see if you can't figure out what x cannot be in these cases. Alright, so in our first one, remember we're kind of saying what is this when it cannot be 0. So we're saying 5 plus x cannot equal 0. So really what we're saying here is x cannot equal negative 5. Now, what about this one when we start to look at what x can't be? So in this case, x here could be any number. If I had 1, 2, 3, or negative 1, negative 2, negative 3, they all have values. But in this case, x cannot be 0. Okay, if x is 0, then I get 0 on the bottom, which means that I run into a problem. Right? Essentially, we're saying x squared cannot equal 0, therefore x cannot equal 0. Now, in our next one, we've got x minus y cannot equal 0. So therefore x cannot equal y. Now in our last one, we have x squared minus y squared cannot equal 0. Now, x squared minus y squared, that in itself is a difference of squareds, right? X minus y, x plus y cannot equal 0. And so we can see from here that, remember, if I get zeros out of these, I can't equal 0, right? So we're trying to figure out what x can be. X can't be y, and x also can't be negative y. So x cannot equal plus or minus y. So plus or minus, just like our quadratic formula, plus or minus y. Okay, so it can have multiple values, and basically we're trying to treat it the same way each time, right? We're trying to figure out what it cannot equal. Okay, now another way to think about this bottom part, just in case maybe you're confused with how I did the factoring that was there, if it helps, we can kind of do the same process that we did earlier when we were solving for x. So if I started with this scenario and I said, okay, I want to solve for x here to see what it can't be, I would move y over to the other side, and I would say, okay, x cannot equal y squared, and then I would take the square root of both sides. But by taking the square root of y over here, see, y is already squared. So if this is like -3, I'm going to get 9. If this is +3, I'm going to get 9. So when I take the square root of x, oh, not there, when I take the square root of x, I still can't have it be plus or minus y. Because regardless of what I plug into here, it's being squared. And so I'm going to get a positive value out, which means I'm going to take the square root of that value, whether it's, say, +3 or -3, +2 or -2. Either way, when I take the square root of a square like that with a number, it's going to be plus or minus that value that it can't equal. Okay? So, great. How many times have I told you not to divide by 0? Just another one of those little jokes. Just showing how, when you try to divide by 0, it creates a lot of issues. So, a rational number is said to be reduced or simplified if the numerator and denominator have no common factors other than 1. So for example, 10 over 15 can equal 2 over 3 when it's simplified down, because I can divide the 10 and the 15 both by 5. Or I can take 30 over 42 and divide each one by 6 and reduce it down to 5 over 7. So similarly, rational expressions are in simplest form or lowest terms when they're expressed as the quotient of two polynomials whose greatest common factor is 1. Now, all of that is to say that we can start to also factor these out like I did that difference of squares earlier. So, to simplify rational expressions, we need to factor both the numerator and the denominator. We need to divide by every factor common to both, and then give restrictions on the variable in the denominator spot. So, we're going to put our factoring skills to the test. I'm going to pause the video here, and this is where we're going to pick up in the second part. There's many examples to come, so the second video is really just going to be examples to go through and to practice different types. So if you have any questions, let me know.